Hi, I'm Joe Strout, and this is Mini Micro. And I woke up this morning thinking about a game where you swing a weight from a string and use that to snarf up targets that are sort of falling past. And maybe there's obstacles that you have to try not to hit. And I've also thought about blocks that if you hit those with the weight, it reverses, bounces off. And so I thought this could be a fun little live coding exercise. So let's dig in and see what we can do. I fired up Mini Micro here. It's version 1.2.1, which is the current version. And where do we begin? Well, let's begin with the editor. We're going to need a sprite to represent the weight, and we'll just draw the string. In fact, I'm thinking about drawing like a glowing arc behind the string, which we'll do as a series of polygons. So we're going to need a pixel layer for drawing the polygons and the string. And then we're going to need a sprite for the circle. I guess we could just draw the circle too, but I don't like that idea so much. I think we'll use a sprite. So let's see. We'll start with clear, display 4 is normally the sprite layer, which is fine. We'll do that. We'll say sprite disp equals display 4. Now let's get a sprite. We use find file. I'm just going to, for now, find a nice circle sprite out of syspics, which we'll probably find in shapes. Okay. Yeah, something like this, circlethin.png will be just fine. I'm going to copy this. All right, so weight equals new sprite. I have a band-aid on my little finger. I don't know if you can see that because I was on a boat last weekend on vacation, trying to get from the boat to a paddleboard, and I grabbed something with my left hand as the board was slipping out from under me, and it ripped my finger, and I needed 5 stitches. So I'm making a lot of typos with my left hand today, but bear with me. Okay, so weight.image equals, let's see, file.load image, paste that path, and add it to the display. Oops, sprite disp.sprites.push weight. And let's run that much. Okay, down here at 0, 0 is our weight. And it actually looks like a decent size. Maybe we'll shrink it down. We could do weight.x equals 40 if we want to get it in the center and see what it looks like better. 640 divided by 320. Yeah, that's probably a good size. I mean, we could play with the scale. You know what? I like that better. Yeah, I think that's going to be better. So we'll actually, let's just copy all this in here as a starting point. Okay, oops, 0.5. Okay, now we want to make it follow the mouse as if it's attached by a string. So I'm going to make an update method. It takes dt, which by default will specify as 0.16, which is 1/60th of a second. No, it's not. 0.16. There we go. Okay, the weight needs a velocity. So weight.vx equals 0, weight.vy equals 0. Okay, so we're going to do basic Newtonian physics here, which means we calculate an acceleration based on gravity and where the mouse is, because we're going to imagine the weight connected to the mouse by a string. It has a certain length, so if it's farther than that, the string is going to pull on the weight towards the mouse. And then gravity pulls straight down. So, and I'm not too concerned about getting the physics on the string exactly right. yeah, those of you who know physics better than me are probably going to be throwing things at your monitor soon, but let's just, it's a video game. It only has to look good and be fun to play. So let's do weight.vy. Let's see. Up is positive, down is negative, so we want to subtract gravity. I'll define gravity up here. Equals, let's see, this would be in pixels per second. I don't know. I'm going to take a wild stab at something. So gravity times dt. So pixels per second is speed, per second is acceleration, and then we multiply it by some number of seconds, which is our time step, and that gets us back a speed, which is appropriate to add to the weight. And I won't worry about the string yet. Let's get this much working. Weight.x plus equals weight.vx times dt, and same for y. Okay, and then while not key at pressed, escape. I can't remember if it's escape or ESC. I think it's ESC. Update yield, spell it correctly, and while. Okay. Nope. It's not ESC. It's escape. Zoink, there it goes. Okay. And that actually looked like a pretty decent rate of fall. So now we have to make it go towards the mouse. So let's get the distance. D equals, if we imported mathUtil, we'd have a function for this. We could just do it ourselves. It'd be square root of some of the squares differences, but we can just do mathUtil.distance between mouse and weight. And if D is greater than, let's call it a chord rather than a string, because string also means like string of letters. It's an overloaded term. That'd be confusing. So chord length equals 100. That's in pixels. All right. So if the mouse is closer to the weight than the chord length, it exerts no force on it. That's like a string trying to push on something. It does nothing. If it's longer than that, it's going to exert a force that should be 0 when it's at the chord length and rapidly increase when you're beyond the chord length. So let's see, force F equals distance minus the chord length squared, probably times some pull factor. And this is in newtons, and now my math is really getting a little rusty, but I feel like this should be a pretty big number. Okay, and then what do we do with that? We apply an acceleration proportional to that towards the mouse. Yep. So I need a dx equals weight.x minus mouse.x, dy equals weight.y minus mouse.y. And then we're going to normalize these by dividing by the length, so that what we have now is a unit vector, a length 1 vector that points towards the mouse from the weight. And now we can do weight.vx is adjusted by dx times dt, weight.vy is dy times dt, and hopefully that'll work. We'll see if I need to actually go look up the physics, but let's try it. Oh wait, I didn't incorporate f. F times that, f times that. I'm not sure about this factor of dt in there. Of course, it won't matter. We could compensate for it by adjusting our force. Oh, okay. It did not work at all. Yeah, it looks like it's actually pushing instead of pulling. Oh yeah, this is a vector that points towards the weight. I wanted to go the other way. Hey, that's not bad. Check this out. Zing. Okay. With very subtle movements of my mouse, I can get that weight really swinging. And I can't very well stop it from swinging. Well, I guess I can. This is not bad, but it does feel a little fast and a little, I don't know, a little too much. Now, one thing we could do is we could actually cap the distance between the mouse and the weight as if the string has a hard limit. But I kind of wanted a stretchy string. I like the idea that, you know, this is you can give it a fling and it'll stretch out a bit and come back. But maybe it's too stretchy. Because if I move my mouse much at all, boy, this thing really goes crazy. Okay, so there's going to be some physics tweaking here for sure. But I want to put in the glowing arc behind it, because I think that'll make it easier for you to see on the video especially. And it'll also be fun to do. So let's see. The arcs are going to be a series of polygons. And they're going to start off strong and then quickly fade out. And when they fade to zero, we'll take them off our list. So let's have arcs as a list. List of polygons. Maybe they should be a list of little objects, because we do need to keep track of like how old they are, so we know. So let's do this. Arc is a class. Arc.points. List of XY polygon points. Arc.age equals 0. Age of the arc in frames. Arc dot update. Let's see, redraw this arc and return false if done. In other words, too old. Okay, so if age, let's see, we should do self.age plus 1 if self.age is greater than, let's try 10, then no, actually I don't want to do that. We'll return that, but let's calculate the opacity of the arc. We want it to start off pretty strong and go quickly to 0. So let's see. Op for opacity equals 255, maybe 200 divided by self.age. Nope, that's not what I mean. 200 times self.age. Oops, sorry. 1 minus self.age out of 10. Okay. I know I've got the magic number 10 in there twice, but I think this will work. So when this is 0, this will be 1 minus 0. We'll get the full 200. And then as age approaches 10, this approaches 1. This factor approaches 0, and our opacity goes to 0. Yeah, that'll work. So now we're going to gfx.fillPoly self.points, RGB, color.rgba, and I'm going to pick a color that's bright blue, 200, 255, oops, 200, 255, with an opacity of OP. And that should do it. Okay. So, our update function then should also update the arcs. So we're going to make a new arc. And it's going to start with points from the previous position of the weight and the mouse. We haven't moved the mouse yet, so we have that, but we don't have the previous position of the mouse. We're going to need that. Let's see, old mouse equals this mouse. This is an easy way to clone a map. Of course, that gives me a lot of stuff I don't actually need, so I'm going to do it this way. Mouse.x and y, mouse.y. And we're going to do that at the end of update as well. Okay, so so our points are going to be the old mouse to the weight position. Again, copying just the X and Y. Okay, that's 2 points. And then we're going to push, after we've moved the weight, arc points that push the new weight position. And the new mouse position. Okay, and then we're going to add this to our arcs. Arcs.push arc. Okay. And then in our update function, well, we could do it here as well. For, let's see, I in range arcs dot length -1 to 0. Don't have to worry about arcs ever being empty because we just added one. If not arcs I.update, then arcs.remove I. Okay, you know, I've never saved this thing. Let's call it, let's see, we're going to swing this weight around and snarf up targets. We'll call it snarf.ms. Okay, program saved. Let's run it. RGBA is not a thing. Well, it is lowercase. Boy, you can tell I was on vacation last week. I've forgotten everything. RGBA, run it. Okay. All right. So our arcs are not arcs.len 0. Our arcs are not erasing, and they're also not getting added to, well, they must be getting added, but they're removing themselves right away. Self.age greater than 10. Huh. Let's do some experiments. All right, arc.points equals, oops. I'm just going to make a big square. 100, 100. Or better yet, triangle, because that's easier. 100, 200, 200, 100. Arcs dot. And let's clear the screen. All right, arc dot update. Return 0. Why? Oh. Right. Okay. Yeah. Return false if done. It's done. Yeah. When the age is no longer less than 10. Okay, this is a little better. Still some funky things going on there. Oh, and we're not properly updating old mouse. Yeah, if we're going to assign to that global, we need to say globals dot old mouse. Interesting. Well, that doesn't look terrible. Let's check our length. Should be, yep, 9. Okay, I think that's basically working. Okay, so let's work on making it a little easier to control, because boy, right now, I mean, I can definitely swing it in a circle when I want to, but I mean, it's going to be snarfing up the entire screen very easily. And I have, yeah, very little control. Like if I wanted to not hit something, if I wanted to slow down and stop, I'm trying to make it go the other way now, and it's just swinging faster. It's got so much energy. So that's not how I want it to behave. Okay. Now I'm asking myself, how long do I want this video to be? Because when you get to this stage of like tweaking parameters and trying to make the feel of a game right, it can take quite a while. So we'll do a little bit, but if it takes more than like 5 minutes or something, we'll call it a day. And maybe I'll do a follow-up video where I get into the actual game. But let's poke at it a little more. First, make sure it's saved. Okay. Now, I've got it so that the force that we apply, which is really the acceleration, and oh yeah, physics is coming back to me. Force equals mass times acceleration. And I haven't really defined the mass of my weight, but it's constant. And so this is really force times mass, which is an acceleration, and then you multiply it by time, and it gives you a speed. So my physics is basically correct. And it's based on the distance, the excess distance beyond the chord length squared, which I'm pretty sure is correct for a spring. But it is quite stretchy. And it means that if the weight gets far away, it's getting pulled really hard back towards the mouse. And then, of course, it overshoots, and that's how it gets going in these really fast orbits. Um, but you know what? It's coding. We can experiment. So let's just try changing the chord force by a factor of 10, say, and just see how it feels different. Interestingly, it doesn't feel that different. It does some. Yeah, I have a harder time making it cover the whole screen now. And it's tending to get into these sort of linear motions. Let's see if I can get it back to a nice circle. Oh yeah, I can. I still don't like that it goes so far out though. Now, of course, we could reduce the time constants and make everything happen slower. We can also increase this factor. What if it's not squared? What if it's cubed? Oh, it really seems touchy now. Interesting, look, it's making kind of a rhomboid. Whoop. I broke physics. Yeah, when you have factors of cubes and such in there, that's not too surprising. Yeah, it looks like as soon as it hits the edge of the string, it really bounces off of it now. Ooh, triangle. So I don't think cube is a good idea, which makes me wonder, what if it was 1? Whoa, now it's really stretchy. I can't even... Okay. Yar, come here. Okay, that's so gooey. Definitely don't like that. 2 does seem the best so far. But the other thing we could do is if the distance is too great, we could cap it. But I don't want to cap it. I want a stretchy string. I just don't want it to stretch too much. Ooh, this is an interesting idea. We could define the tension. Let's do that. Let's define the tension on this string. And we'll put that on the arc. This will make it prettier anyway. And so we'll have the tension be 255 times self.tension. Okay. And we're going to put, let's see, arc.tension will be Matthew Till. Well, I was going to use clamp, but I don't really need to use clamp. I can just say D out of chord length times 2. If arc.tension is greater than 1, then arc.tension. Actually, we'll leave it like that. So I'm pretty sure RGBA will cap. Let's try it. Color RGBA. What if I tell it 500? Normally these should be from 0 to 255. Yeah, it returned FF. So values greater than 255 are just treated the same as 255. So the tension is whatever it is, but now we'll be able to see the tension because it's going to turn more red the further it goes. Hey, that's kind of pretty. Okay. Oh yeah, and there's still a lot of blue in there. I should actually reduce the blue. But it's just going to be red all the time because once this gets going, Yeah, you almost never release the tension on the string. Interesting. Okay, but let's make it pretty by turning down the blue. Let's put this in a new line. So the red increases with tension, the green is constant. The blue is going to be 1 minus self-dot tension, and the opacity is what it is. Oh, look at that. Pretty orange. That's because I had the green in there. So when it's fully red, it's not fully red. It's red with a little bit of green, which is orange. So I need to take this down with the blue. Blue factor. Whoa, okay, there we go. Okay. So yeah, but in practice you would just do this, cover the whole screen, and it'd be red the whole time. And in fact, once you've done that, it's quite hard to stop. Oh, what about some drag? Yeah, every physics simulation needs some drag. And drag is, doing drag properly is hard, but doing drag game style is not that hard. We're just gonna reduce the velocity or apply a force opposite the velocity that's proportional to the velocity squared. So let's see, v squared equals weight vx squared plus weight vy squared. I should be doing this before we apply the velocity to the weight. All right, and this is getting long. Let's add some comments here. Gravity, chord force, drag. Okay. So in this case, F equals V square times drag force, which we're going to define up here. Not sure what that should be. Probably not that much. Okay. All right, weight Vx. Let's see. Do I need a normalized vector here for Vx and Vy? Probably. If I don't, then I'm already multiplying by the Vx and the Vy. So, so let's do V times. I am so mangling the units here, but it's okay. All right. So we're subtracting from Vx a factor of Vx itself. This may be way too much, now that I think about it. Because if this f is greater than 1, I think this is way too much. Yeah, 0.1 makes a pretty draggy weight. Whoa. And then we got a nan. We broke physics. So I think we need to cap this f. Okay. Hey, this is better. This is actually much easier to control. And if I wait with that drag force on there, just take my hands off, it will come to rest. Oh, you know what? I should actually draw the string. I'm not doing that. Let's do that. After we update all the arcs, we're going to GFX draw line from mouse to weight, color.white. Oh yeah, you can't do that. Got to specify X and Y separately. So mouse X, mouse Y, weight X, weight Y. Ah, nuts. We're leaving some screen trash behind at the ends of the line. That makes sense. Polygon wouldn't necessarily include those. All right, this is getting close to quitting time, but old mouse X, old mouse Y, weight X, weight Y, color dot clear to clear that line. Whoop. Okay. Yeah, so here we go. We can swing this around. It still gets going a little fast. I don't love that about it, but it's way more controllable than it was before. And I could imagine getting into a groove where you're snarfing up targets and dodging ones that you don't want to hit. If you move the mouse too quickly, it should break the string. That'd be a nice refinement, but I don't know. Yeah, there may be something here. And I think it's a good start to a game because I'm having a lot of fun just doing this, and I kind of don't want to stop. But anyway, that's it for today. Let's do a quick review of the code, and then we'll call it a day. So we've got about 80 lines of code here. We import math-util. We do our setup of the display, setting up actually clear sets of all the displays. We get a reference to the sprite display. We make a sprite and initialize it to the center of the screen. We define some constants. Then we make a class to represent the arcs, each of the arcs that trail behind the string. They have points, age, tension, and an update method. And then we keep a global list of arcs. We keep track of the previous mouse position every time through. And then here's the meat of it. It doesn't quite fit on one screen. But we erase the old line. We start making a new arc. Then we do some physics, applying gravity, applying force from the cord, applying drag, which I forgot at first, but that's super important for keeping your physics from blowing up and making it easier to control. And then we apply the velocity to the weight. We update our last arc, push it on, and then we draw all the arcs and the new line, and that is it. Here's our main loop. It just calls update. If I really wanted to do this right, I would calculate the time step and pass it in, but right now what's going on is quick enough that I'm sure we're getting 60 frames per second. So this factor here, 0.016, will be about right. And that's it. I hope you've enjoyed this. If you have any questions, leave them in the comments below. And if you go to miniscript.org, you can find a link to our Discord server where I and lots of other friendly Miniscript folks are hanging out, and we'd be happy to talk about it with you. Till then, happy coding.